wall, and this is my lab report on the motion of a falling Slinky. The purpose of this lab is to analyze the vertical motion of a Slinky from static equilibrium and evaluate it as it falls to the ground and determine whether the bottom of the Slinky remains motionless or not. I use Tracker for my experimental model, GlowScript for my computational model, and Google Sheets to create a graph that compares these two models. I am interested in the results so I can analyze a real-world example of Newton's second law in effect. The physics principles include Newton's second law, which includes the velocity update formula, the position update formula, and the splitting of net forces before the top hits the bottom and after the top of the Slinky comes in contact with the bottom of the Slinky. In the first case, the net force includes the tension from the Slinky and the force of gravity. After it hits the bottom, the net force is the sum of the gravitational force and the drag force, which acts in the opposite direction of motion, which in this case is the upward direction. I use Tracker to find initial conditions for my computational model. I set the coordinate axis as the bottom of the Slinky, and then I base the model off the 1.7 meter tall man, the blue shirt guy in the picture, the dark blue shirt. For my initial conditions, I found the object weighs about 0.2 kilograms, and the drag constant is about 1.11 based on trial and error. I know the velocity is initially 0 because it starts at rest, and I've been told that the Slinky starts at static equilibrium, and so the net force is also 0. For my coding, I created two while loops, one before the top hits the bottom and one after it hits the bottom of the Slinky. In the first while loop, the forces of tension and gravity are opposite and equal to each other, since they are the components of the net force, which is 0 at static equilibrium since velocity would remain constant. In the second while loop, when it hits the bottom, the net force includes the force of gravity and drag, which are not equal and opposite. The position is going down, meaning the downward force is greater than the upward force, hence the gravitational force is greater in this case. This is my graph on Google Sheets comparing the computational and experimental models. The variations that can be seen between the two models is mainly due to human error, as the general flow of the models is similar and shows the motionless aspect of the bottom of the spring initially. At the end of the experimental model, there's leveling out, as can be seen in the blue graph in the tracker, which is caused by the impact with the ground. However, it doesn't happen in the computational model since there's no ground for the object to fall on. In the beginning where position is constant, you can see as long as the tension exists, which is equal and opposite to the force of gravity, the forces are canceling out and the bottom does not move. In the future, I can improve the data by finding a more accurate form of measuring the point mass in tracker instead of just clicking the frame and causing a potential inaccuracy. I could have also split the model into multiple masses for greater accuracy, meaning I could have modeled the Slinky from the top as well in addition to the bottom. Lastly, I could have found a more analytical way to calculate drag instead of just using guess and check, which would have allowed for less variation for more accurate measurements, which would have allowed for more accurate models. Thank you for watching.